Welcome everybody to our video solution to problem 3 from quiz 11, spring 2023, Math 302 at Cal State Fullerton. All right, we're given a commutative ring with identity, call it R, and we want to determine whether, it looks like 4 different statements are true, false, or sometimes true. So, and we don't need to explain our answers, but well, I'd probably say a little bit of something. So these first two, they actually form a nice little pair. Every prime ideal of R is a maximal ideal, and every maximal ideal is a prime ideal. So what we saw in class is that maximal is a harder condition to meet than being prime. So if you're prime, you may not be maximal, right? Because it's harder to be maximal. But if you're maximal, then for sure you're prime. So it's definitely true that if you're maximal, then you're prime. That's true. But the other statement, the converse, isn't necessarily true. But sometimes it is. So for example, if you're working in the integers, then every prime ideal is a maximal. On the other hand, let's say you're working in the ring of polynomials with integer coefficients, and you look at the ideal generated by x squared plus 1. So this was an example we did in class. So this is an ideal. This is prime, but this is not maximal. All right, so this is sometimes true. All right, what about the third one? We have 3 ideals, A, B, and C. And we know that A divides B, and we want to determine, does A have to divide BC? So if these were just numbers, then this would be a true statement, which suggests to us that this really should be true, and that actually is correct. This is true. And we can give a little argument for it. Now, for those of you not in the class, the definition that we've been giving for divisibility of ideals is, it's not the most general definition, but it's good enough for the situations we have in class. So our definition has been that A divides B if and only if B is a subset of A. Right? And at least in the situations we've been looking at, that's fine. So in our situation, then, if we want to show that A divides BC, we would need to show that BC is a subset of A. But this is actually quite simple because BC is a subset of B. Ooh, why is that true? Well, remember, B is an ideal, which means it absorbs multiplication. So if I multiply by anything in C, it will still be in B. And then if I add up things in B, it's still in B. So BC is a subset of B, which is already, we know, a subset of A, because A divides B. And so we conclude from this that A divides BC. So just for a little extra clarification, if you were using the more common general definition for divisibility, right? So this would be kind of our version from class, but we could do a more general version. We could say, okay, A divides B if there exists, well, I'll skip C, how about an ideal D? So this is an ideal of the ring such that B is equal to A times D. And that should remind you a lot of the way we do divisibility for numbers. All right. Well, we want the same thing for BC. All right. If A is going to divide BC, then we would need that BC is equal to A times something. Okay, but if we know that B is equal to AD, well, that implies that BC is equal to AD times C. And at this point, you would need to know that you had associativity of multiplication of ideals, which actually that's a true statement. So we could rewrite this as A times D times C. And I've now shown that BC can be written as A times an ideal. Okay, so once again, we'd get A divides BC. Okay, cool, so that's a true statement. Finally, every ideal R in the ring R contains an element, little r, such that curly r, the ideal r, is generated by little r. Okay, this was just a game. See how many times I could write r in a different way in the same problem. All right, so this is basically saying every ideal is a principal ideal. And of course, we know that there are situations where that's true. They're called principal ideal domains. The integers are a good example of that. But there are also examples of rings which are not principal ideal domains, like Zx. In fact, we saw in the previous problem that Zx has an ideal which is not principal, right? Namely, we looked at the ideal generated by 3 and x. Okay, this is not principal. Okay, whoop, we misspelled it. Not principal. Okay, and so this one is going to be sometimes true. All right, so none of these statements are actually always false. Fantastic. All right, we will see you next time when we talk some more about equivalence relations.